Hi, grade 11s. Today we're going to look at the first real meaty lesson of the quadratic functions unit. And tomorrow you'll have a work period on this, and then we'll really get into it when I get back at the beginning of October. So, looking at properties of graphs of quadratic functions. So let's look at a situation here. Okay? The situation that we're looking at is we have a football is kicked into the air from the ground. The table below states the height of the ball off the ground at different times. Okay? So what we want to do is we want to take a look at this table here that tells us the height at different times. So at 0.4 seconds, there's a height of 4.7 meters. 0.8 seconds, there's height of 7.8 meters. 1.2 seconds, height of 9.4 meters. 1.6 seconds, height of 9.4 meters. 2 seconds, 7.8 meters. 2.4 seconds, 4.7 meters. Graph the points, estimate the maximum height the ball reaches and the time it takes to reach it. So time goes from 0.4 all the way up to 2.4 seconds. So we've got 20 ticks here. Now if we have 20 ticks, then we should probably say that maybe that this is, I don't know, that would be too much even. I was going to say that this could be 1 second, but that's going to be too much. If I go 1, 2.5, that might not be enough. So what we'll do is every 2 ticks is 1 second. So that's 1. Every 2 big ticks is 1. So that's 1. That's 2. That's 3. That's 4. That's 5. So this is time. Okay? And now, as far as the height goes up to maybe about 10. Not 100% sure. So, but 10's a good estimate, so we can say, okay, well, then that is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is height, so that's h. Okay? So now what we're going to do is we're going to plot these points. So at 0.4 seconds, we go up to 4.7 meters. So 0.4 would be like about here. 4.7 would be like right here. Then we have 0.8 seconds, and that would be 7.8. So that's like right there. At 1.2 seconds, we're going to be about as high as 9.4. So that's going to be like right here. At 1.6 seconds, which would be like right here, we're also at about 9.4. At 2 seconds, we're at 7.8 again. So that's going to be like right here. At 2.4 seconds, we're looking at 4.7 meters, which is right here. Now, so what's this graph going to look like? Well, we know it starts on the ground. And so what we can do is we can graph this part of the graph right here, for sure. And that happens at the next interval. So I know that after another 0.4 seconds here, 2.8 seconds, this is probably going to hit the ground again. So 2.8 would be like right here. So I can draw this part of the graph too. Now parabola looks like this. Or like this. So what we need to do is we need to just realize that it's going to go maybe up a little bit more and then down. That's going to be, so this little piece right in here is just something that we're adding because we know that this is the way a parabola goes. Okay? So that's what the graph is going to look like. Now it says estimate the maximum height. Now this is going to be an estimate because, first off, it's off our graph, but we need to take a look at what this would be. Well, this would be about, if I take a look here, that's maybe about another half or 0.6 maybe not even 0.6 because it's a little bit up there. If we take a look at that, that's really maybe about another half. So it's probably a good estimate to say that this maximum height is going to be approximately 10.5 meters. That's just a guess, okay? Now the time it takes, we can actually do better than just estimate, because we see that we have at 1.2 seconds a height of 9.4 meters. At 1.6 seconds a height of 9.4 meters. Now a parabola is symmetric. Now what that means is that it is the exact same on both sides. So I can take this right here and draw a line right through at 1.4 seconds. And now we have, this is where the time is. So it's going to be at 1.4 seconds. We know that that is the time at which it reaches its maximum height. The maximum height itself is an estimate, but the time is not. And we see the symmetricness. So what I'm going to do is I'm going to take a look at this right here, and I'm going to make this a different color, maybe purple. And I'm going to go from here to here. From 0.4 seconds, it's the same distance from here to here. Okay? I don't know what this is. We're just going to get rid of this. Now we're just going to get rid of this. Okay? So right here, this here is the same as this here. And maybe just to be easy here, this here, this time length here, is the same as this time length here. Just like this time length here is equal to this time length here. Okay? In this case, it's 1.4 seconds. It's 1.4 seconds. In this case, it's 1 second. It's 1 second. In this case, it's 0.6 seconds. It's 0.6 seconds. And in this case up here, it's 0.2 seconds. It's 0.2 seconds. So this line of symmetry cuts the parabola in half perfectly. And it happens that the parabola looks identical on both sides of this line of symmetry. Alright? So we're going to talk about a couple things. First, we'll talk about the axis of symmetry. The axis of symmetry, or the line of symmetry, is a vertical line that divides an object into two equal parts. A quadratic function's axis of symmetry passes through the vertex. Okay? What's the vertex? Well, the vertex is the maximum or minimum point on a quadratic function. So going back up here, I'm going to do a little bit of erasing here. Actually, that's not what I want to do. Okay. Here's the deal. Here's the deal. This point right here is the vertex. The vertex is the highest or the lowest point on the graph. Now, what we're also told is that this axis of symmetry is what goes through the vertex. This axis of symmetry, it has an equation. Its equation is going to be x equals whatever this number is here. Now, this number right here, we already said is 1.4. So the axis of symmetry for this particular quadratic function is x equals 1.4. Okay? Alright. So there's a couple little bits about quadratic functions, talking about the vertex, the highest or the lowest point. And also the axis of symmetry. The axis of symmetry passes through the vertex. Okay? Alright. Now let's do another example. The daily profit, P, an ice cream stand earns is a function of the price they charge C per ice cream cone. So P equals, and actually, I buggered this up. If these are x's, then this ought to be an x here too. So change this to an x. Okay? P equals negative 25.8x squared plus 180.6x. What's the maximum daily profit for the ice cream stand? What price should they charge to earn the maximum? So use a table of values to find your answer. So, okay, so how do we do that? Well, best way to do that is to type this into your graphing calculator. Okay? Type in y equals negative 25.8x squared. So go to your graphing calculator. Go to y equals. Oopsies. Go to y equals. Type in negative 25.8 x squared plus 180.6x. 180.6x. So now once you have that typed in here, the graphing calculator is very slick. It allows you to graph functions, but it also does something really nice too. It can generate a table of values for you. So what I want you to do is I want you to go to second table set, and I want you to go starting at 0 and go up by 1. If those aren't set to 0 and 1, then change them to 0 and 1. Then when you're done that, go second table. What this does is it tells you a table of values. So what I can do then okay, I don't like that, but anyway, I'll live with it. See if I can do this a little bit here. Maybe, maybe not. I'm going to cheat. Just for the sake of making this easier for me, I'm going to take a snapshot of this, go edit copy, bring it to my lesson, so I don't have to flip back and forth. Right click, I'm going to paste it, there we go. So use a table of values. So anyway, this is our table of values. This is nice and slick, because this is your x value, this is your p value. We're interested in seeing where the maximum is. Now, what we have to understand is, going back to this example here, what we know is that if we take a look at this graph, if we have values and they keep going up and up and up, and then all of a sudden they hit the same amount, and then they start going down and down and down and down, you want to look at those two values that have the same y value. Because the vertex, or the maximum value, or the minimum value, depending on the context of the question, is going to be between those two values. Okay? So going back to what we have here, now, what we're going to do is we're going to look at where we have the same values. Now, we have the same values right here. So what I know is the x value that maximizes the function is going to be between 3 and 4, halfway between 3 and 4. So x is going to be 3 plus 4, halfway between. So I'm going to divide by 2. So 7 divided by 2. So x is going to be 3.5. Now x represents the price they charge. So that's going to be $3.50 for an ice cream. Okay? Now, what is that maximum daily profit? Now we don't know that, but we do know that if we plug in 350 into this equation here, then we'll figure it out. Now, again, we can go ahead and do this the hard way if we want to, or we can do this the easy way. If we do it the easy way, then we go back to our graphing calculator and go to second, oopsies, I gotta erase that. We go second, it's annoying, second table set. Now, instead of going up by 1s, if we're going to go up to 3.5, then we can go up by 0.5s. And I can even start right at 3 because I know I'm interested in 3.5. So if I do that and I go second table, then I see, oopsies, second table, not graph, I see, and I'm very interested here, at this value right here, at 3.5, the y value is $316.05. So going back here, I know that P of 350 is going to be $316.05. And this value here is going to be the maximum value. That's the maximum profit. So we should make some kind of a therefore statement. Therefore, the ice cream stand should charge $3.50 to make a maximum daily profit of $316.05. Okay? All right. So now, that's how we do it. So again, this is the beauty of the graphing calculator. The beauty of the graphing calculator here, guys, is that the calculator does the work for us. The only real calculation I did in this whole darn thing was I did 3 plus 4 over 2. Everything else the graphing calculator did for me. So when we say that we're able to solve more complex or real-world problems with the graphing calculator, that's exactly what I'm saying. If we learn how to use the graphing calculator properly, then it helps us do our job a lot easier. Next example. Use the table of values to graph the function y equals x squared minus 3x minus 10. Find the intercepts, the equation of the line of symmetry, the vertex, and the domain and range. So it's x squared minus 3x minus 10. So going back to our equation here, now I have to clean up my mess. Now I'm going to go back to my y equals, and I'm going to kill this equation, and I'm going to type in x squared minus 3x minus 10. There we go. Now I need that table of values. So to do my table of values, again, I go second table set. I should probably start at maybe -3, and I'm going to go up by 1, so I don't need to go up by 0.5s. So if I go second table, gives me this. So again, I'm going to cheat. That's edit, copy, bring it over here, right click, paste. There she is. There's my table of values. So I'm going to use this table of values to help me graph this function. So I see that I have y values of -12 right here, which tells me that my minimum is going to be between 1 and 2, and my minimum value is probably going to be a little bit lower than -12. So I'm going to go from -20 to 20 on my y scale. So to do that, I'm going to go up by 2s. So that would be 4, 8, 12, 16, 20, -4, -8, -12, -16, -20. And then on the x's, I can easily go just -5 to 5. So I'm just going to go 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. So if we graph this, we get what? Well, -3 and 8. Where is that? Well, it's going to be like right here. Chunk. -2 and 0. Right there. -1, -6. Right there. 0 and -10. Right there. 1 and -12. That's right there. 2 and -12. That's right there. 3 and -10. That's right here. And if we follow the whole idea of the symmetricness, then 4 would be -6. 5 would be 0. And it would go like that. So what we're going to do is we're going to see it's going to be some lower value. We don't know where this minimum value is, but we know that the minimum value, the x value that the minimum value is going to be at is 1.5. So I just need to plug in 1.5 into this. And again, I can do it on my own, or I can let the graphing calculator do the work for me. So I'm going to go to this, and what I can do is, heck, I can even just look at the graph of this. Now, if I look at the graph of this, I see that's cut off. So I need to go to my window, and I need to make my negative value here, maybe, I don't know, negative 15 will do. Now I hit graph. And I can easily calculate the minimum here. So second, calc, max min. I have to pick a min, because it is a min, so it's option 3. Now it asks for left bound, so left bound would be right here. So press enter, and then you just want cursor past that minimum value. So I'm past it now. So I'm going to press enter again, and it's at 1.5. The minimum value is negative 12.25. So going back here, I know it's negative 12 and 0.25. So that might be like, oh, I don't know, like maybe like right there. So what I'm going to do is I'm going to get something that looks like this. There we go. So that's how we graph that. Now it says to find the intercepts, the equation of the line of symmetry, the vertex, and the domain and range. Okay, so intercepts. There are 3 intercepts in this question. They are here, here, and here. So the x-intercepts are at negative 2 and 5. The y-intercept, there's always only one, is at negative 10. The equation of the axis of symmetry, well, first off, we know the vertex is negative 1.5 and negative 12.25. And piggybacking off that, the axis of symmetry is x equals whatever that is. So x equals negative 1.5. The only other thing we're missing is the domain and range. Now, this is a parabola that opens up. So as such, the domain is going to be, now how we write domain is, we haven't done this for a while. Basically, it's all real numbers. So we can say that by basically saying it goes from, that's not what I want. We can just use round brackets here and go from negative infinity to infinity, which tells us that it's all real numbers. Now the range, it's not all real numbers because there is a minimum value. With the range, the minimum value is right here at negative 12.25. But it goes from that minimum value, so we use square brackets because it includes that point. We can't use square brackets around the infinities because infinity is a concept. It's not an actual number. So it doesn't include negative infinity to infinity. But the range includes negative 12.25. And it's going to go all the way up to positive infinity. Okay, so the range goes from negative 12.25. It includes negative 12.25. So we can use square brackets. It goes up to positive infinity. But we cannot say infinity is the number, so we have to use round brackets around the infinity. Okay, moving on. Last example. A snowball is thrown into the air from the top of a building. The height above the ground y in meters is related to the time x in seconds using the following formula. Y equals negative 4.9x squared plus 15x plus 5. Graph the function using technology. Find a snowball's maximum height to the nearest tenth of a meter and at what time it reaches its maximum height. State the domain and range. So, here's what we need to do. We need to take this and type it into the graphing calculator. So we need to go to y equals, we need to nuke what we have here. We need to type in 4.9x squared plus 15x plus 5. Then what we need to do is we need to come up with what we think is an appropriate window. Well, if we're talking a snowball, the x represents the time, so we're going to start at 0. Probably not going to take more than 10 seconds, so we can go up by ones. And what I can also see, and I can cheat here because I can see that my graph is here. I can actually see that that's 1, 2, 3 seconds, and that's a 4 second. So I can actually go here and actually even just go up to like 5 seconds. Now if I go here, I'm going to start at 0, and 10's not big enough. How about 20? Is 20 going to be big enough? If I press down, I see that it is. It is big enough, so that's wonderful. So now I can go ahead and take a look at what that maximum point is. So I can hit graph here, and I'll see it right here. Now, I'm asked to find the maximum height and the domain range. So what I need to know to graph this is I need to know where this maximum height is and where the 0 is. And I know that I should know this point. If I don't, I can hit trace, and it's going to tell me, oopsies, I can type in 0 here. And it's going to tell me that's 0, 5. So it's going to start at 5. Okay? So if I go back here, I know that I'm going up to 20. So I can say that this is 4, 8, 12, 16, 20, and my x values can go up to 5, we said. So that's 1, 2, 3, 4, 5. So 5 would be right here. This is 1 point. Now if we take a look at here, what's this point right here? That's what I want to know. Well, to figure out that, we'll use second calc, and we're going to go ahead and pick a 0. So that's option 2. Use the left bound, so we got to go over a wee bit. That's at 1, 2, 3, 4 seconds. So I'm going to pick 2.5 seconds. You can just type in the time. So 2.5 seconds is right here. This is to the left of this point. Now the right bound, I'm going to pick probably 4 seconds. Press enter. And it's way over here, so we're good. So press enter, and it tells me the 0 is at 3.36 seconds. So where's that going to be here? Well, this is 3.5, 3.25. It's going to be like right about right. Didn't mean to do that. Going to hit this. Now I'm going to go at about here, give or take. Okay, so this is at 3.36. So I'm just going to put a label here, 3.36. Now I just need to find out the coordinates of the vertex. Now the coordinates of the vertex I'm going to find by going second, second, calc, maximum now, because we're looking for a maximum, and the left bound's not way over here, so we're going to have to type in, I type in like x equals 1. And it's right here, so that's good. So the right bound we can just cursor over because we're pretty close. So you're just going to keep cursoring until you get past that hump. And we go right about here is fine. Press enter. It says guess. Press enter again. And we get 1.53 seconds. 1.53 seconds. So going back over here, 1.53 seconds is going to be like right here. What's that maximum value? It's 16.5 if we round. So 1.53 and 16.5. So that's going to be like right. Ooh, that's going to be like right about, because that's 18, that's 17, that's 16.5 would be like right here. 16.5 would be like right here. So to graph this then, we would just go from here. We're already kind of all on the way up. We get to that maximum. Then we come all the way down and reach that. And I can probably do a bit of a better job drawing that in. So I'm going to try here. This needs to be the maximum, and then it needs to come down through and touch that point. There we go. There is the snowball's path. Now, it did say if we set the nearest tenth of a meter, so this would be 1.5 and 16.5. So it's at 1.5 seconds it reaches a maximum height of 16.5. So now, state, domain, and range. So the domain are the possible times. Now in this case, because we're not talking about an equation, we're talking about a situation, the time starts at 0 and it goes to when the snowball hits the ground. Now the snowball hits the ground at 3.36 seconds. So the domain is from 0 to 3.36 seconds. And I suppose if we're going to write that to one decimal place, that would be 3.4 seconds. Now the range goes from obviously a height of 0, that's the lowest the snowball can be, up to a height of 16.5 meters. Okay? So there's your domain and there's your range. Because we're talking about something contextual like a snowball, there's going to be a maximum, there's going to be a minimum. Okay? And we can't talk about negative time or negative height when we're talking about a snowball. Alright? Okay, your homework is on pages 368 to 372 in your book, numbers 1 to 16. You have a work period tomorrow, and I will see you in October.